In this slide, we will see naive Gauss elimination, which is used for the large number of systems. This is actually basically an elimination of systems again, which we saw in the previous slide. And this is just an extension of it for a large number of equations. And what we need to do is simply we again eliminate some unknowns so that we can have a single equation with one unknown, so that we can use it to find that unknown and use it in as a back substitution in the previous equations. So also division by zero must be avoided in this Gauss elimination. If the zero division is not considered or ignored, it is called naive Gauss elimination. If there is a consideration of this zero division, then it is called regular Gauss elimination. It has two algorithms. The first one is forward elimination of unknowns to reduce the equations to an upper triangular system. So simply you can see that from here we move it to here, so that in the last equation, for instance, we will have only one unknown here, x3 for instance. We find it, then we back substitute them into the previous equations. So here we found it, then we back substitute it to the second equation, find x2, then back substitute this to the first equation here, find x1. The primes indicate the number of times that the coefficients and constants have been modified. The first step of the naive Gauss elimination is forward elimination of unknowns. And in this, as we said earlier, we try to have an equation which has only one unknown in the end. And here, for instance, we have a general set of n equations. You can see what we need to do is we need to start from eliminating from the first term, and this for the first equation, the first term constant here is called the pivot element. Actually, the first equation called the pivot equation, and a11, which is the first term, is called the pivot coefficient or pivot element. This is important because we start from here. To have an upper triangular system, we will have simply a triangular system, so we need to eliminate the terms over here. So we need to first eliminate the first unknown x1 from all other equations. So in the first one it will remain, but in the others we will eliminate x1s first. So that's why this is called the pivot element, the first one which has to be eliminated. So to do this, we multiply the first equation by a21 divided by a11 to have. So basically we remove this by a11, but we multiply by a21 so that we can have the same as the second one, and when we subtract them from each other, we will eliminate x1 from the second one. So simply when we multiply this by the first equation, we will have this equation, as you can see here. In here we only have a21. Now we can subtract this equation from the second equation, from this one. Then we will have, so simply you can see a21 x1 and a21 x1 will be eliminated, but in the second one we will have a21 divided by a11 times a12 minus a22, or the opposite, a22 minus this. And the remaining terms will be the same by subtracting the remaining ones, and the last term will be b2 minus this one. Or we can simply say that these are new coefficients, like this one is a22 prime, and this one is a2n prime, and this is b2 prime. That's why we can write simply by prime values here. So these are the changed coefficients. Then we repeat this process for the remaining equations, meaning that we simply subtract this from the remaining ones. So then actually this will be wrong, not this one, but we multiply the first one first by a31, because here we have a31. Let me write a31 x1 like this. That's why we multiply this by a31 divided by a11. Then we will have such an equation like this. Then we will subtract that from the third equation. If we subtract that, we again eliminate the first term, and we will have this third equation with the nil prime coefficients. Similarly for fourth and up to nth equation, we will have the same, and we will this way eliminate the first equations here, you can see. Now we can repeat the procedure for the remaining equations, and we will have these final equations. After this, what we need to do is we need to continue on multiplying. Now we will multiply by a prime 2 2 divided by a1 2, so that we can eliminate this this one a prime 3 2 divided by a2 2 prime, so that we can eliminate x2 from this third equation. To have a triangular system, we need to eliminate this now. So let's continue on the next slide for these operations. In this slide, we continue on forward elimination, and we want to eliminate the a2 from the third and the other remaining equations. And for that, for the third equation, because we have a prime 3 2, we divide it by a2 2 prime and multiply it by the second equation and subtract from the third one. We repeat this by simply multiplying by a4 2 prime divided by a2 2, multiply by this, subtract from the fourth one, then do the same for fifth and the rest up to the nth equation. Then we will have this, as you can see, we eliminated x2's from the others, and we started to have this triangular system. We repeat this for the third equation now, and we want to just multiply a double prime 3 4 divided by a double prime 3 3 for this equation, and subtract it from the fourth one, and do the same for the rest. Repeat this process, and we will have finally an upper triangular system, as you can see here. And the final equation will have only one unknown, so that we can start solving from here. You can see. And this, in here, the double prime, also in the rest, it will be triple prime and 4 prime. These will indicate again the modified elements. So after this, as we said, we will start solving from here, and we call this process back substitution. By substituting to the previous equations, we will find other equations or other unknowns. Let's do that in this in the following slide. After the forward elimination step, we will have the back substitution step, and in this we will start from the last equation of the upper triangular system, because we have only one unknown here. When we solve this, you can see that we can obtain xn as just isolated version of it, bn n minus 1 divided by ann n minus 1. So we obtain this. Then we back substitute this into the n minus 1 equation. So put it here and find xn minus 1. Then put it back here along with xn. Then find xn minus 2 and etc. So that we will have a repeated process by back substituting all the calculated unknowns up to the first equation. And we will have finally all the unknowns. And this repeated process can be represented by a general formula that we can write here. xi is equivalent to bi I minus 1 minus summation j plus 1 aij I minus 1 xj. I and j are the column and row values, numbers of the matrix, let's say, or the constants, these ones, I and j basically, and as the denominator I minus 1 for I n minus 1 n minus 2 up to 1. So this is the common equation that we can use. We can simply actually use a now algorithm to be able to have naive Gauss elimination as a computer code, for instance, because this can be coded easily to solve equations. In this slide, you can see the algorithm for naive Gauss elimination. In the first one, actually, the forward elimination pseudocode you can see here. Simply, we will have a division because we said that we actually divide the second term by the first term so that we can have the second equation first term as equivalent to the first equation first term, and we eliminate the second equation first term from here. And do the same for the remainings by using this value. And after this factor is the division actually, and subtract the equation constants, and do the same for the last the b constants. Let's say this is a x b. Simply we apply the operations here and as well as here, so that's why we have this here as well. So simply we have three nested loops. The outer loop moves down the matrix from one pivot row to the next, this one. So starting from the first pivot element to the next. The middle loop moves below the pivot row to each of the subsequent rows where elimination is to take place. So basically we perform the elimination using this factor value. And the innermost loop progresses across the columns to transform the elements of a particular row. Basically we make this subtraction to eliminate the constants from each row. And on the right hand side you can see the other pseudocode for back substitution. And in the back substitution our formulation is this actually. We need to just simply implement this. And in here we have the first equation, the last equation which has only one unknown, xn, and we've calculated by bn divided by ann, and this is done only once. After this we need a for loop to be able to calculate these. We simply back substitute this to the previous equations. And we have a sum here, a temporary variable, to accumulate the summation. Here you can see for bi's. And we will have a for loop here to be able to have this summation again by simply calculating this one, sum minus aij xj, this one. And also we have a division here, this one. So this results in somewhat faster execution time than if the summation were accumulated in bi. So this sum is actually creates a faster execution time. More importantly, it allows efficient improvement in precision if the variable sum is declared in double precision. So we use double precision for sum to be able to have an efficient calculation. But if you write these in MATLAB, for instance, then you can simply use naive Gauss elimination for any number of equations.